Welcome to the Daily MBA, where business wisdom is served fresh and fast, straight from one of the top MBA programs in the world. I'll give you summaries of my lectures and readings, as well as the most important insights gained from an MBA, so you can apply all of this knowledge in every business. Let's get started. On today's episode, I'll start talking about something relatively new in my episodes, and it's stats, or the proper word, statistics. So I know many people don't like math, and probably that's what scares them from an MBA, but stats are going to be crucial in any type of career that you want to pursue, because I believe stats are the type of math that we are actually seeing in real life all the time, because stats are related to means, to variations, to regressions, and how some variables may be related to the behavior of other variables. So stats is going to be a very important tool, and in my episodes, I'm going to try to break it down for you so you're not worried about all of the weird math part, but also understand about the logic and the applicability of stats into the real world. But of course, as every first step, we first have to learn some of the basics of stats in order to then apply it into the real world. And so it may seem like we're going to do some weird things, but this first episode is going to be explanatory of some of the important concepts that we should learn in statistics. So first thing is that I wanted to tell you that all of the successful managers are going to always gather, analyze, and interpret data better than others. And for this, they're going to use three things that is going to be descriptive data analysis, which is going to be basically showing all of your information into dashboards. Then second thing that you could do is predictive data analysis, and this is going to be forecasting into what's going to happen in the future. And then the last type can be prescriptive, and this one's going to be a data-driven decision-making, and is, for example, when you do A/B testing or things where you're testing with data that's going to tell you what is going to be the best choice for your business. So as I'm saying, all of this will be very important, and in stats, where the stats play into all of this, this will give us the statistical inferences, the regressions, and the applications of how we use all of the data into doing all of these things. So our basic framework for any statistical analysis is going to rely on an important concept, and it's that we don't have the data on the population, but we only have data for samples that we can take. And so if you think about it, this is going to be logical. You can only measure, for example, if I do a big survey and measure the behavior of people in banks, I'm not going to have the entire population's behavior. I'm just going to have a small sample, and what we want to have is that this sample will have statistical significance over the population, and that means that my measurements for the sample are going to be able to provide me valuable information about the population. So the weird thing about statistics is that we're going to differentiate all our symbols when we're talking about the mean, the variance, and the standard deviation when it's in a population, that would be the big total, versus in our sample, which is what we have. But so there are usually three questions that we may ask ourselves about the population mean. The first one would be an estimation. So what is the best guess estimate that we can take from the population mean based on what we have from our sample? And this question is going to be the easiest of all of them. And this one, why is it the easiest? Because basically your big population mean, we're going to assume that it's going to be the same as your sample mean. So this is going to be your point estimate, which is going to mean your best guess to what is your population mean. So this one, we already have it covered. We have two questions remaining. First, we may also want to know what interval of information will contain the population mean with a certain amount of probability. So now let me put all of this in normal words. Let's say, for example, or what interval will have this mean with a 95% of probability. This is just narrowing it down. And it's making sure that you don't have the exact number, but the exact number will fall somewhere between a range that you will give. And this range is going to be called the confidence interval, and we'll be studying this in one of my future episodes. The last thing is going to be hypothesis testing. And this will probably take you back to high school, but this is going to be talking about what is the probability that a population mean is either equal to or greater or less than a specific value. And so for all of this, we're going to require statistical inference. This is not going to be as easy as the first question. So now that we have these three main questions that we want to know, I'm going to move on to talk about another topic, and it's the probability distributions. So as you may know, there are many ways in which variables can behave, but we're going to focus on the two most important ones, and they are going to be called the Bernoulli distribution or the normal distribution. And why are we only going to do this two? Because basically they are the most popular ones, so we're going to see them over and over and over again. The Bernoulli, it's the easiest one, and this one is only going to be applied for binary numbers, so only zeros or ones can be in this distribution. The normal one is going to be for a continuous variable, so for example, what is the height of people? We're going to see that that one is going to be a normal one, and normal distributions usually have a bell shape, so they're going to go up and down. In the middle is the mean, but then you also have some tails in each of the corners, and this is going to be symmetric. This is the second type of distribution. So let's summarize before I move on to the next thing. Bernoulli is going to be for the distribution of binary numbers, 0 or 1, and then the normal one is going to be for continuous variables. And so, now that we already know the original distribution, I'm going to start talking about another crucial concept that we need to learn, and it's the sampling distribution of the sample means. So this is going to be, let's say, I'm going to put an example so this starts making sense, that I'm going to interview 100 persons and we'll get their average height. So this is going to be one mean from my sample. So I already have that measure. Now let's see that I'm going to interview another 100 and I'll take another average, so another mean, and I'll start doing this experiment over and over and over again. And I'm going to start plotting not the people's heights, but the means, and this is going to be called the distribution of the sample means, because it's the distribution of probabilities of all the sample means, which were the ones that you would obtain if you drew repeated random samples. And so this distribution is going to look at the variation across the sample means. And this is important. We're not looking at the variables, but at the distribution across their samples. So usually you would only have one sample mean. But if you create a distribution of many sample means, then you can make an approximation of where the population mean would be relative to the sample mean. And so this may sound ambiguous, but what are we saying? Like, if we only have the mean of one sample, we're not going to have the best results as if we had lots of samples and we already had all of the means of those samples. And this is going to give us a better hint of how things look. So the distribution of sample means, it's always, and this is an important theorem in stats, going to look as a normal distribution after many samples are drawn. So with many samples, I'm going to repeat this because it's crucial, when you take many samples, the sampling distributions of the mean become normal, so they get a bell-shaped. And so this is called the Central Limit Theorem. And this means that when the sample number is large, the distribution of the sample mean, as I was telling you, will be like a normal distribution, but this is going to be regardless of the original sample distribution. So remember, I was telling you maybe we may have a Bernoulli distribution or we may have an uniform distribution. It doesn't matter, because however it used to behave when we plot all of the sample means, and we do it over and over again, it just can't be 10, it has to be a big number. This is going to look like a normal distribution. So I'm going to do a short pause over here just to go over important concepts that I've been talking. First one is going to be, we're always going to assume things about population based on the samples that we have. Second, we can have original values behaving in a specific distribution, and I told you the two most important ones, or the two that I would analyze, would be Bernoulli or normal distribution. And then the third thing that I was explaining is the distribution of sample means. And this one's going to be different. It's when you're plotting all of the means. And this one, when it's large enough, will always behave like normal distribution. So I hope you're following me up to here, because this may sound ambiguous, but when I'm putting real-life examples, you'll see that this becomes applicable in everything. So those are the three main differentiations, and that's why you have to develop this stats vocabulary to not get confused. The last thing that I'm going to mention in today's episode are going to be three important properties from the distribution of sample means. And so I was already giving you some hints on the first important property, and this is going to be that the mean of the sample will always be the mean of the population. So this is an assumption that we always have to make, and will make our life way easier because we don't have to think that means are going to be different. What is going to be different is going to be the standard variation, because the standard variation of a sample is going to be the standard variation of the population, which is usually represented by the letter sigma, and then we're going to divide that by the square root of the sample size. So sample is going to usually be represented by an n, and so I'll put over here one formula of the things that I'm talking about, but the standard deviation of the sample will depend on the standard deviation of the population divided by the square root of the sample. And then the last thing that we have to consider is already the theory that I gave to you. Sampling distribution, when the sample is large enough, will always behave like normal distribution. And so I don't want to scare you getting into more jargon, but next time we're going to keep studying some of these basic things around stats so we can start making all our statistical inferences, and we can get to all of the possible uses of stats in the real world. So I'll see you next week.